So, I mean, that's hard for the in the first day, fundamental, and then the afternoon session. People are tired, maybe. But
Yes,
you will make it.
It's a day.
Mhm.
It's a very dense presentation.
Okay, again. I think. All right. But yes, but as we know it. Okay. So, yes, I think for the last turn this afternoon, two presentations, two lectures to come, both from Orléans, which is very nice and appreciated. So I like to introduce Jacques Poirier, who is, I think, well known in the refractory area. For those who are not so, will maybe coming new to this field, I learned a lot in fields of corrosion, etc., from you already. So he's, I think, yeah, well established person in fields of corrosion, and his topic is the modeling versus laboratory and industrial experiments. So you learned about some fundamentals about the scaling, and I think Jacques is from, let's say, the atomic scale, maybe till the big plants and big parts. And the stage is yours.
Ladies and gentlemen, welcome to the extraordinary world of refractory modeling and testing. The menu is the following: as starter, a brief introduction, why model and test, then as main course, modeling and testing, first for the manufacturers, formulation and design, for the researchers, establish models, understand degradation mechanisms, for the users, expertise, and improvement of refractory performances, and as dessert, a brief conclusion, the future of modeling and testing. So, the first part, as a starter, just a brief introduction, why models and test. What is the main importance? The important is to have good criteria for the best selection of refractories. The first approach is an empirical approach, but by combining different approaches, fundamental aspects, laboratory test and modeling, industrial appraisal and process data, we are very useful to take a French look on the issue of refractory selection, giving rise to approaches completely different from empirical approaches. But what is the specificity of the laboratory test and modeling for refractories? The experiments are very difficult due to high temperature. There is a strong coupling between thermics, mechanics, transport, and corrosion. And we have really complexity of the associated phenomena. So it requires an in-depth expertise. But we are lucky. Why? Because we have new advances in the laboratory characterization of refractories and models. The combination of models and the high-performance experimental techniques with powerful digital tools makes it possible to access information that have been inaccessible directly. Here you have an example of the determination of the elastic and inelastic properties at high temperature using integrated digital image correlation. What are the advantages and the limitation of laboratory and experimental experiments? Modeling. We can use phenomenological or multi-scale models. We are able to simulate physical conditions. We have a wide range of calculation codes: thermodynamics, thermal, mechanics, fluid flow, multiphysics, different software, Fatscape, Sage, Thermocalc, Abacus, ANSYS, Console. But the main difficulty is that we have a simplified modeling of reality. and we have a difficulty simulating real and coupling stresses in a complex environment. What are the advantages and the limitations of laboratory tests? We can use standard tests and advanced tests in situ experimented. We have a very well controlled of the different parameters, but we are typically in a simplified condition in use with a small scale and a very short time. Concerning the in-plant testing industrial and process data, we are in real conditions for a long time, but we have a fluctuation of industrial parameters, atmosphere, temperature, variation of temperature slag, with different and combined different stress conditions, thermomechanical, thermochemical, and we have a real difficulty to implant and to analyze the results. Now, as a second part of my lecture, I propose to you the modeling and the testing for the manufacturer, mixing raw material, pressing, and sintering. Just look at a quick remember about the design of refractory materials. A refractory materials is composed of aggregates and of one matrix. So aggregates are composed of coarse grains, and they are made of several minerals which induce the principal characteristics of the refractories. The matrix represents 30% of the material. It is composed of fine grains with additives, fine and ultra-fine powder, which reflects the specific characteristic, plus a bond, which ensures the cohesion of the system, plus an open porosity. This addition phase, which consists of the porosity, represents between 10 and 25% in volume, and it is very important to the behavior of the materials. Just a quick remember about the refractory manufacturing process of shaped refractories. We have 3 stages: crushing and mixing raw material to optimize distribution and packing design. We have grains, and we have small grains and fine particles that fit the space between the large grains. Pressing to achieve the highest grain density, and sintering to bond particles at high temperature. What are the models and tests for refractory manufacturing process? Concerning crushing and mixing raw material, we have to optimize the distribution with different models, particle packing model, like furnace model or Dresden models, are very classical models. Pressing, we can use compaction model, and sintering, we have a lot of different possibilities. Sintering model, thermodynamic models, dilatometry test, shrinkage measurement, and standard test, density, porosity, cold crushing strength, and so on. Just look at an illustration of models for refractory manufacturing, a compaction model. Here you can see a refractory title. It is a refractory bricks with a very complex shapes. So it's very difficult to get in all the materials an optimum compaction. The green material is a granular material. The granular material deformation has 2 parts, an elastic deformation, very low, and a plastic deformation. And we have adopted a macroscopic approach for simulation with an equivalent homogeneous material. Here are some details of this compaction model. We have an elastoplastic behavior law. We have used a modified Camcray model. This model is very well adapted to minerals and especially to clay materials with an elliptical yield surface we can define the hydrostatic pressure, the deviatory stress, and we can determine the model parameters with two types of tests, shear trial test and hydrostatic compression test. But what is the impact of the tidal shape on the compaction of the refractory materials? Just look at two examples. One, shape 1, no groove. Shape 2, grooves all around the titles. We use the abacus. The numerical model take into account the rigid body of for mold, plus contact, plus symmetry. It represents only half title. What are the results? Here you have a mapping of the density of the materials. We observe in these two shapes, 1 and 2, a significant impact of shape on title density after shaping. This figure represents the density versus the thickness between hot phase and cold phase. And we observe, especially for the shape 2, that we have a great variation. So we are able to describe the compaction behavior of the material, tracking of heterogeneous area, and to optimize the homogeneity of the density. The second example concerns the sintering and a continuous sintering model. The continuum theory of sintering is very well known with this following equation, which defines the stress-strain rate tensor and the sintering stress. We have an equivalent deformation behavior with the relation between the stress and the strain with a linear viscous law. We can take into account the creep with the Norton creep law, which is, of course, a nonlinear behavior. And we have to determine three grid parameters: creep viscous parameter, shear modulus, and bulk modulus. So we are able to describe the sintering of the material. But this type of model is mainly used for technical ceramics and advanced refractories. A second point concerning sintering is to better know the thermochemical reaction during sintering. And we can use fact stage or thermodynamic to calculate the condition of multi-phase, multi-component equilibria. And I propose to illustrate this use by an example controlling the sintering process of mullite zirconia bonding refractories made from zircon and andaluzite. Major point is to understand and to predict the role of secondary oxide addition, especially sodium oxide, titanium oxide, and phosphate oxide as sintering aids. To simulate, we consider 1 mole of this secondary oxide addition, and we observe on this figure the amount of phase, especially the liquid phase, versus temperature. And typically, we have a strong but negative effect with high amount of a glassy phase for sodium oxide, which is undesirable for matrix sintering. Typically, at 1550 degrees C, we obtain 6.6% of liquid. Titanium oxide is a suitable sintering aid with a lower amount of liquid, and phosphate oxide has a slight retarding effect of the liquid formation. These information are obtained by calculation, and they are compared with the evolution of the microstructure and the porosity of zircon alumina andaluzite mixture after sintering at 1550 degrees C. We have a comparison without addition and with sodium oxide addition. We observe that we have a decrease of the porosity, but we have a really negative effect with a notable amount of amorphous phase. The liquid phase causes densification of the matrix and reduce the open porosity. The zircon is completely dissociated after sintering when we use titanium oxide additive, and the porosity is reduced. It's a very benefit effect. And concerning the phosphate oxide, the decomposition of the zircon is marginal. However, the open porosity is reduced. So from this information, we are able to understand the role of the secondary oxide addition, which provides an optimum combination, which is here 2 mole of phosphate oxide and 3 mole of titanium oxide, to optimize the green properties and to have a complete dissociation of zircon at high temperature. And you observe the optimal microstructure which is obtained. So thermodynamic modeling is very useful in optimizing the formulation. But we can also use laboratory measurement, and especially the shrinkage measurement, which is very useful for the formulation of refractories. So here you can observe the effect of the shrinkage for the same products at different sintering temperature. We observe a decorrelation between the aggregate and the matrix, and a significant matrix shrinkage when we are at high temperature. So it's not acceptable for the formulation of refractories. So how to avoid the matrix shrinkage? By employing additives, here pianites, and this figure represents the volume change versus the ratio pianic andesite. You see a very great impact of pianic, of the volume expansion, and also of the porosity of sintering mullite zirconia matrix. So we are able to define the good ratio to adjust in to obtain zero shrinkage. Now, I propose you a second aspect of modeling and testing. It's the use of model and test for researchers. And the important activities in research is the prediction, that means to establish model, and of course, understand degradation mechanism, corrosion, thermomechanics, thermochemical mechanical couplings, to be able to propose optimized formulation, optimal design of refractories. But if we observe the refractory degradation in industrial situation, we observe that we have a lot of different mechanisms: rupture, fusion, erosion, spalling, corrosion, impregnation, neural phases transformation, thermal shock. So all these degradation needs to implement tests and models in the field of corrosion, thermomechanics, and thermomechanical couplings. Just look at corrosion modeling and testing. Here you have another industrial example. It concerns secondary metallurgy, the OH or OHOB, which refining steel. We observe the refractory at different scales: industrial facilities, refractory lining, refractory bricks, and microstructure. And we observe that we have a complex phenomena involving the chemical transformation of the refractories. And we need a multi-scale approach in a factor of 7^10, from the 10 meters to the micrometers, if you want to be able to make the good choice. So to understand the corrosion of these refractories, we can make corrosion tests in lab. Just some example of different tests in laboratory. We have static test, dynamic test, pill test or disc test, crucible test, induction furnace test, corrosion by alkaline, corrosion by oxidative gas. We have tests with rotary slag, rotary furnace test, test with rotary finger, that means rotary furnace test. So many standard tests. But what is the objective of this test? They give a very, very, very limited information. So the only information is to compare different material in the condition of lab and not in the condition of industry. So it's very limited, it's very poor. So we need, for advanced corrosion testing, to better study corrosion. Here you have an illustration of an experimental method based on the principle of finger corrosion test. We use an induction furnace with a controlled atmosphere. We use fingers. Here you have an example of magnesia graphite fingers after corrosions. These refractory fingers are immersed in a crucible containing two phases, steel and slag, and the melting of the steel is carried out by induction heating. And the samples are rotating, so we are able to simulate the erosion. You measure the wear of the refractories by measuring the change in the slag composition. The slag is regularly withdrawn every 10 to 20 minutes, and we determine the evolution of the composition of the magnesia in slag, which is correlated with the corrosion of the refractory versus time. And the analysis of magnesia content, for example, by X-ray fluorescence, make it possible to follow the corrosion progress of carbon magnesia refractories. We obtain two very important information. The interpretation of the mechanism is carried out by observation with scanning electron microscope on the corroded fingers cooled after corrosion. And the kinetics of corrosion is determined by the evolution of the composition of the slag. We have just here an example. The evolution of the composition of magnesia in slag versus time, and we have a linear evolution. But it's very, very important to study the microstructure after and before corrosion to determine the evolution of the microstructure and the phase change in its use. It's very important to understand and after to limit the corrosion. Here you have an example of a steel ladle, and we observe a sample. We observe different zones of attacks with different texture. The slag, a precipitation zone at the interface between slag and refractories, an impregnation zone, and the refractory as used. But the interpretation is very, very difficult. Why? Because the mineral phase observed at room temperature are not really representative of those observed at high temperature. Here is just an example. The laboratory test was made at 1,600 degrees C. We observe the microstructure after cooling and the microstructure after quenching, which is representative of the microstructure during the test at high temperature. And we observe that these two microstructures are different because we have recrystallization and transformation during cooling. Consequently, the information is very limited. But the concept of local thermodynamic equilibrium allows us to interpret the microstructure. If we observe here this interface between the slag and the refractories, we have, of course, chemical exchange, we have not in a global equilibrium, and we have a gradient of composition in the volume. But if we consider a very small part of the refractories just at the interface, the solid-liquid reactions are faster than chemical transport. That means that we can apply the concept of local equilibrium, and locally, the chemical potential of each compound is equal in all the phases. That means that we can use the thermodynamics and fact stage. Why? Here you have the microstructure at room temperature. We can make a mapping, an EDS analysis in very local zones. We can introduce this composition in the thermodynamic software. We can fix the temperature, or we can make an evolution of the temperature, and we can calculate it, the phase at high temperature, at equilibrium, liquid phase, and solid phase at high temperature. Look at this example. We have the microstructure, and here we have represented at 1600 degrees C at the interface, the slag, the precipitation zone, the impregnation zone, and the refractories, the solid phase which are in equilibrium at high temperature, hexaluminate of lime, corundum, mullite, and we have determined the profile of composition of liquid phase at high temperature. And we are able also to determine the viscosity and the profiles of viscosity during the corrosion. And we observe a really increases of this viscosity. That means that the zone of impregnation is very limited in this high alumina refractory. Now, what are the mechanisms of the parameter of corrosion by slag? We have 4 mechanisms. First, capillarity infiltration of slag in the porosity. You observe the impregnation of the bauxite refractories in contact with liquid phase, and the key factor is the capillarity tension due to the weighting of refractory by the slag. The second mechanism is a mechanism of dissolution of oxide on the surface of refractory. You observe here a dissolution of magnesia into slag in a converter. And here I have represented the law of the dissolution, which is the Nernst law, which depends on 2 factors, kinetic factors, diffusion coefficient, and the limit of saturation of the compounds of refractory in the slag. The third mechanism is the erosion of the corroded surface by moving liquid in contact of the refractories. We have the friction forces, slag is in motion, and we have the erosion of the surface. We observe here an erosion of the fine particle in a magnesia graphite matrix, and the last mechanism is the surface protection by precipitation of slag deposit. We have dissolution and precipitation of solid phase during corrosion, which protects the refractory. The main question is, what are our possibility to experiment and to model this mechanism? For each mechanism, we are able to model the permeability, the erosion, the corrosion, and to make laboratory tests to measurement the porosity, the viscosity, the erosion of the refractories, and also the prediction of the phase of the kinetic models. Just look at. Here it's a capillarity infiltration of refractory by slag. What's happened? In contact with slag, we have a surface phenomena which becomes a phenomena of volume. is due to the reactive infiltration of an aggressive liquid. We can define the equation of the transport of this liquid under saturated impregnatation, which is driven by capillarity forces. And we can define the parameters of transport, viscosity, capillarity pressure curves, porosity, intrinsic permeability, or relative permeability. And we are able, by measurement, to access to these parameters. Gas permeability measurement gives the possibility to access to the permeability of the liquid. We can determine the capillarity pressure curves. We are able to determine to measure the slide viscosity by aerodynamic measurement. The second mechanism is a mechanism of dissolution, precipitation of oxide on the surface of refractories. It results as a gradient of chemical composition at the liquid refractory interface. The dissolution rate is gauged by the Nernst law, which depends on the saturation limits and the kinetics of dissolution precipitation. The saturation limit is the thermodynamic data. We can obtain the value by phase diagrams or modeling. As example, on this figure, we represent the alumina and the magnesia saturation versus the lime-silica ratio in secondary metallurgy slag, and we observe a real difference between the solubility of alumina and the solubility of magnesia. The kinetics of corrosion is very important. We access to this information by lab experiments. Just look at here an example of kinetic of dissolution of alumina grain in alumina lime slag. The experiments were made by X-ray diffraction in situ, an observation of the microstructure, and this figure represents the evolution of the weight fraction versus time. We observe a decrease of the alumina, a dissolution of the alumina, but we observe also the precipitation of new phases around the grain of alumina, hexaluminate of lime, and dealuminate of lime. And we are able to model this experimental value, and you have here a curve. We represent the experimental value and the modelization of the kinetics of corrosion. The fundamental aspect is that the calcium and oxygen ion diffuse from slag through the monomineral layers of the refractories. Now, concerning the erosion of the corroded surface by moving liquid. What is the effect of slide stirring on the refractory work kinetics? It's very important to quantify this effect. So we use a corrosion laboratory test. We measure the evolution of the magnesia in slag, but if we observe, we have an eccentric rotary magnesia carbon finger. That means that the rotation speed of the finger varies. So what's happened? We have made here two experiments, a rotation of 35 rotations per minute, and we observe a whirl rate which is 1.24% per hour. We modified the speed of the rotation, and we observe that if we increase the speed, we increase the work. That means that there is a real effect of the erosion on the work of refractory. But, which is very funny, if we observe our finger after test, we observe that we have an asymmetrical work of the finger. You observe the initial finger and the geometry of the finger after corrosion. Why? because in the front phase, the movement speed is totally different than in the external lateral phase, in the internal lateral phase, or in the back phase. And the difference on speed of the slag in contact of our refractory shows that the work is totally different. But you can say that it's only laboratory test. Look at what's happened in industrial application. Here, we have an extrapolation of our lab test to a steel ladle, and we obtain realistic result in comparison with lab test. First, the speed does not exceed 25 centimeters per second in the surface of the metal. We have used fluent software to simulate the flow of slag and steel, and we observe that near the magnesia carbon slag line, the maximum speed is above the porous block closest to the wall. In the bottom, we have 3 porous blocks, and which are in this figure. And from the lab experiment and from this industrial modeling, we are able to predict the effect of slag stirring on the refractory work kinetics in the steel ladle, in industrial case, and this figure represents the work of magnesia graphite refractories per heat of slag line versus the amount of iron oxide in slag. We observe that we have a strong stirring, we have a low level of iron oxide, we have a very good desoxidation, but we have a high work of refractories. And when we have a low stirring, we have an important 10% of iron oxide in slag, and the refractory have a low work. Now, I would like to speak to thermodynamics, modeling, and testing. A quick reminder about the thermomechanics of refractories. We have 3 major characteristics: a nonlinear and elastic behavior. These curves represent for the magnesia graphite refractory stress as a function of strain. And we observe, it depends on the temperature, but we observe a really nonlinear and inelastic behavior. The second characteristic is a non-symmetry in tension and compression behavior. Here, it's an alumina graphite refractory, and it's a stress-strain curves in tension and compression. And the third effect is the relaxation phenomena, viscosity and plasticity. As an example, here we represent the viscosity of the box side versus temperature. And we have a very great evolution of the viscosity as a function of temperature. So, to describe the behavior of the refractories, we need a consecutive equation. We have very simple equation if we want to describe elasticity or thermoelasticity, but we can also introduce plasticity and viscoplasticity, and also we can introduce viscoplasticity with damage and phase transformation. But we have an increase of the degree of the complexity of the model if we introduce all these different phenomena. Simple models does not take into account certain physical mechanisms, viscosity, plasticity of transformation. Any simplification of the behavior law can lead to erroneous results. Here you have an example of a comparison between model of experiments for resin-bounded magnesia graphite products. We observe, this figure represents stress versus strain. The model is composed of 3 parts. a law of elasticity coupling with damage, the boundary domain which describes the appearance of inelasticity, and the evolution laws for damage and permanent strains. And we have a good correlation between experiments and model. Now, let's speak about the thermo-mechanical coupling. The refractories degradations are very complex, including a force pattern, transport, thermics, chemistry, and mechanics. So we have to take into account to select the best refractory, thermic aspects, transport, transfer of matter, chemical reaction phase change, and mechanical aspects, which are interlinked with relatively strong coupling. That means that we have to identify the physics, to prioritize couplings, and to identify different scales. So just 3 examples. The first example concerns a bauxite brick in steel ladle. So you have a view of the bricks, and we observe that we have a great impregnation by silica, titanium oxide, iron oxide in several centimeters. That means that in the zone which is impregnated, we have thermoplasticity. And the consequence is a tensile rupture of the impregnated layer. If we represent in laboratory the creep rate versus temperature, we observe that we have an increase of the plasticity after slag impregnation. That means that we have a good correlation between industry observation and experiments in lab. The second example concerns the dolomite in AOD, argon oxygen decarburization converter. We observe circumferential compressive strains on the hot phase and damage of the hot phase. Why? Because we have at the hot phase precipitation of silica-lime compounds, and the effect of this precipitation is an hardening of dolomite at hot phase. This figure represents the creep rate versus temperature before and after impregnation, and impregnation after use. And we observe an increase of hardening after slag impregnation. The third example is not in steelmaking. It concerns the combustion chamber of waste-to-energy facilities, incineration. We use a silicon carbide titles, which are in contact with external cooling system and metallic casing. So, in contact with this title, we have fly ashes. This silicon carbide lining covering metallic tubes in which high-pressure water circulates to produce after electricity. Here it's a model which was implanted in finite element code Abacus, which predict the in-service behavior of silicon carbide title in an incineration. First, we have the thermal profile. Then we determine the oxidation rate, which depends on the gas transport and kinetics of reaction, and we deduce the effect of this oxidation rate on the thermomechanical binding of the titles. We observe deformation. And we are able, by modeling, to determine the evolution of traces. Here it's the vertical traces in the title versus time. And it's a very, very long time because it's practically 1 year. And this evolution is totally in agreement with the observation. Now, what is the main advantage to use modeling and testing for the user? We have 3 main challenges: expertise, improvement performances through masonry design and wear prediction, and the use of data mining to predict the wear evolution of refractories and to adapt the refractories to the evolution of the process. First, expertise. Here you have a block of burners of a metallurgical furnace. What we observe? We observe radial cracks and we have a densification of shrinkage and cracks. If you work in the yield of refractories, you have to improve this situation. Why? By modeling. But we have a very, very small available data. Just elasticity modulus, cold crushing strength, and the history of temperature and boundary conditions. So we use a very simplified model. Here you can observe the results of this model. We observe a good quantification, correlation between observed cracks and numerical modeling, radial cracks and during cooling and heating. So you are able to determine the hot zone apply, lift, and you observe a normalization of the refractories. So now we are able to propose solution. First, modify the rise in temperature, heating, and the temperature decrease, cooling, or modify the choice of refractories most suitable, low expansion, better creep resistance, low elasticity modulus. The second case is to develop models to optimize flow geometries, ensembles, and structure. We have two types of model: flow pattern, heat transfer, and temperature distribution by fluid mechanics, or temperature distribution, trace, and deformation in all types of structure by solid mechanics. That means that we have to use different software calculation, for example, Fluent to compute fluid dynamic or finite element analysis for the structure. But what are the limitations? First, the wide variety of material and situation, a strong thermal mechanics chemistry coupling. Just look at some example. Here we have a thermomechanical modeling of refractory structure and pieces, heating wall of coke oven, crucible for blast furnace to optimize the geometry of the carbon block, and here the continuous casting to optimize the shape of the refractory lining. Another example concerns the CFD modeling for the optimization of the tapered canals. The objective is to increase the basic oxygen furnace availability, which can be achieved by minimizing turbulence of magnesia graphite tapered canals. We observe here two simulations. A CFD simulation of a turbulent kinetic energy in the case of cylindrical taper and conical taper, and we observe that the conical taper decrease steel turbulence and lower nitrogen pickup. And in practice, we increase the lifetime of refractories of a ratio of 50 to 17%. So it's very important. So another aspect is, of course, for the user, the prediction of the wear of refractories. As illustration, I propose you just an example, the corrosion of magnesia graphite refractories in basic slag for flat products and aluminum kiln. We have here a steel ladle, and we observe here the slag line, which is in a contact with different slags, which are liquid, and we have a really composition fluctuation between 20 to 56% of alumina and magnesia in this slag. In metallurgy, in steel making, the composition of these slags are not really well controlled. So, what we observe in laboratory test, this figure represents the wear rate of magnesia graphite versus the ratio lime alumina in slag. We observe that the corrosion rate rise when the lime content of slag increase. Then we observe a maximum of work for a ratio lime alumina around 1.54. Then, beyond, the corrosion rate drops quickly as soon as the slag content disperses lime crystal. Once the value of 1.6 is reached, the ratio of corrosion is divided by 2. That means that at the level of laboratory, we have key factors to limit the corrosion of magnesia graphite by improving the control of the composition of the slag. If we introduce magnesia in the slag, we observe the effect of the saturation of magnesia in slag. We decrease the corrosion and the effect of magnesia contact is really effective. Between 5 to 10% of magnesia, the corrosion rate is divided by 2 or 3. And if we compare this laboratory to industrial result in steel ladle, the same tendencies were found. Here, this figure represents the work rate of magnesia graphite in steel ladle versus ratio lime alumina slag after aluminium desoxidation of steel. That means that we have a really key parameters to decrease the work of magnesia graphite slag lime by playing on lime alumina ratio. And concerning the magnesia, it's the same effect. Here we observe in the steel ladle a decreases of the performances, and when we introduce addition of magnesia in the form of dolomite, magnesia lime, we observe immediately an increases of the performances. The addition of dolomite allowed to reduce the corrosion of magnesia graphite refractory by slag and to improve the performances. Last point, so for me a very important point, in steel making and in other application of refractories, we have a lot of data. We have a really data mining in mean, in standard deviation, often in real time. What are these data? Temperature, thermocycle, frequency of reheating, chemical composition of steel, oxygen activity of steel, chemical composition of slag, solubility limit in slag, viscosity, flow rate, gas, thick iron, steel, slag, scrap metal loading, intensity of steel stirring, atmosphere pressure, oxygen blowing, partial pressure, gas pressure, inclusion cleanliness, daily production, capacity of production, duration of metallurgy treatment, continuous and terminal operation, raw materials, steel grades, metallurgy treatment, and so on. So these data are very important to improve the refractories by the process. Just look at an example of data mining. It concerns the carbon pickup of ultra-low carbon steel. So ultra-low carbon steels are very important grades for steel making, and typically the amount of carbon in this steel is 30 ppm of carbon. And here we observe a strong correlation between carbon pickup for ultra-low carbon steel and magnesia carbon refractory wear rate in steel ladle. And the carbon pickup is approximately between 10 and 20 ppm. It's very, very important in comparison with the composition of the steel. So we deduce that the work of magnesia graphite slag line in the desoxidized slag plays an important role in the transfer of carbon to steel. But why? If we observe the refractories, just take at the slag line. We observe the slag. We observe the inclusion of metal into the slag. We observe the magnesia graphite with a decarburite zone, and we observe a very thin magnesia carbon dense layer. Magnesia dense layer. Why? If we use the process data, we observe also that we have a great correlation between the carbon pickup and the iron oxide in the slag. That means that the correlation between refractory works, process data, and quality of steel is not a really clear correlation. And between an iron oxide of slag, which is very low, and only 4% of iron oxide in slag, we have a difference of carbon pickup of 10 ppm. What's happened? In our refractories at high temperature, the pressure partial of oxygen is very low, typically 16 minus power 10 atmosphere. At high temperature, we have a carbon reduction reaction, and we have the reduction of magnesia by carbon, and we form magnesium vapor. What's happened? First case, if the slag is just a little oxidized. In the presence of iron oxide in the slag, at the interface, the magnesium vapor in contact with the iron oxide in the slag form a magnesia. We have a formation of a dense layer of magnesia with a very positive effect of the corrosion, and we have a limitation of carbon pickup. Second situation, the slag is not really oxidized. That means that we have not iron oxide in the slag. At the interface, we have no condensation of the magnesium vapor. We have no formation of a dense layer of magnesia, and we have a high carbon pickup. So, to conclude the dessert, what are the future challenges for modeling and lab and experimental experiments? Big data and artificial intelligence. There are really cost-effective opportunities to improve knowledge and find innovative refractory solutions. The second aspect is developing new experiment techniques at high temperature, in situ, multi-scale characterization, multi-physical characterization. For example, viscosity measurement of aerodynamic levitation, structural identification by Raman, NMR spectroscopy, synchrotron radiation, determination of corrosion kinetics, Raman cartography, and so on. It's also to develop industrial experimental. Why? Because installation of industrial instrument and process allow to validate large-scale results obtained at the laboratory scales. Thank you very much. We have no time for our exercise, but you can make it at home.
Yeah, thanks, Jacques, for this very dense presentation or lecture. Multiple examples, I think, yeah, I can just encourage all of you. You have a presentation on USB stick, so you might follow, and yeah, we recorded everything, so it might be possible to rearrange. It was a lot of stuff. Thanks again for this talk.